¿Qué tal? Muy buenos días.
Good morning. Welcome back. I forgot to thank Miquel Iturbe for his fantastic presentation. And now we're going to be hearing from Pedro Peris López, who was also selected for the JNIC seminar, the event which in Spain is the benchmark for cybersecurity researchers, and organized together with INCIBE as well to promote R&D and I. And this particular presentation today was selected for that event. He's going to tell us on how electrocardiogram systems, ECG systems, and those streams, data streams, can help for continuous authentication. Good morning. Thank you very much for that kind introduction. I'm going to start with a little bit of background about myself. My name is Pedro Peris. I am a lecturer at the Carlos III University, and I work with cybersecurity in e-health, and lately very much as well with implanted systems for e-health, together with Carmen Cámara, one of the co-authors of the piece of research that was the start for this presentation. She's currently doing research in Oxford, which is why I'm here on her behalf to deliver this presentation. So let me start with what I call our motivation. Why is it that we've been doing this type of work? And I just want you to understand first what we mean by implantable medical devices, IMDs. You've probably been reading in the press the so-called implant report, or that controversy. Is this connected with that scandal or not? Well, we'll see about that. What is an IMD? It's a device implanted. That means that I would carry it in my body permanently, although there are systems where part of the system is implanted and part is worn, not actually implanted in the body. What do they treat? Well, very often cardiovascular pathology, or when there is a severe tremor. And why are these devices implanted? Because of treatment purposes. Plus, we can then monitor continuously the patient. And in future, those individuals will not just be monitored, but also new capacities will be added. Who knows? Improving memory, for instance, in Alzheimer's patients, for instance. Why is this good or bad, positive or negative? After listening to Miquel, he was telling us about industrial environments. What's the difference in this case? Well, in this case, we're not talking so much about security, but safety, individual patient safety. That would be the core for us. That would be our main purpose, keeping the patient alive. So please remember that during my presentation. And bear in mind as well that we're talking about electronic devices that can also be attacked. For instance, the FDA in the US clearly state these devices and systems can also be attacked. So what should be done? What should manufacturers do to improve security and safety of these devices? Logically, safety and security should be included from the beginning of the design. What was wrong about the internet to start off with? It gives us all these new possibilities and capacities, but it wasn't terribly secure to start off with, which is why we need to patch it up time and time again. So these new technologies and systems, that's what's been done in the past. They've been patched up, which is not great because we're not just talking about IT security, but individual personal safety. That's critical, isn't it? I would also like you to bear in mind during my presentation that I'm not going to be talking about science fiction, but about systems and devices that are currently used by many people. So, implantable medical devices, IMDs. What's the background? What's been done in the past? What does the future look like? Here we can see a timeline up on the screen. The first pacemaker was first implanted when? Well, quite a long time ago. In 1926, there was the first proposal for something like a pacemaker. Was that an implantable device? It wasn't. Look at that poor patient with all those gadgets around him. One of the main landmarks was in the 1960s, when the first devices that were still pretty big were small enough to be implanted, truly implanted. There would be other landmarks, but let's move on to 2006, which is when wireless connectivity was first incorporated. So, implantable devices with wireless connectivity. That's a huge paradigm shift. Previous devices couldn't communicate with the environment unless you were in a very, very short range. There are many different devices. For instance, pacemakers, the ones that are best known. Why? Because they were the first ones to come, and also because thinking about pathologies that humans suffer, cardiovascular pathology is by far, well, not by far, one of the most common pathologies that would require these devices. Then other devices in this group would be neuro simulators. The difference here is that catheters, shall we call them wires, in this case go to a particular type of the brain depending on what you need. The main difference between pacemakers and neuro simulators is that neuro simulators are a little bit dumb compared to pacemakers. They transmit a current to that particular whatever type of the brain, part of the brain, whereas the pacemaker monitors your heart so that when it goes too fast or too slow, only then, there and then, it will act. Neurostimulators are differently, mostly because of our level of knowledge of the human body. We know how the heart works better, much better than the brain, so we can simulate that much more easily to then diminish certain symptoms. Not constantly, though. And then I have here up on the screen insulin pumps. We know that these devices are becoming much more common. In this case, the device is partly implanted. The controller of the system is not implanted and only catheters are. And this is an interesting device because thinking of the implant report, journalists, after their research, came up with a report analyzing medical devices, not just IMDs, but other medical devices, including prostheses. But in fact, they found that insulin pumps are one of the systems that seem to fail more often, partly because of the way they operate. So again, insulin pumps very popular these days, and unfortunately they seem to fail far too often. I mentioned earlier that it was in 2006 when wireless connectivity started for these devices. And you might be wondering, why is it that important to have full connection and continuous data streams for these systems? Well, one of the motivations has to do with costs. Thinking about healthcare management and costs, these systems reduce costs because patients need to go less often to the hospital or to their specialist. Instead of going once a month, for instance, well, they would go less often, and that would cost less, and it would improve their quality of life. Also, patient monitoring can be continuous. The pacemaker, for instance, can be transferring data non-stop so that the doctors can check, and thanks to machine learning capabilities, there would be an alert if something goes wrong. Logically, that means that patients can be managed much better, and early detection can happen far more easily for different problems. And yet, very often we find still now that they continue to work in an isolated manner, whereas in the near future, all these different devices will be able to communicate amongst themselves, transfer information from one to another much more easily. Wireless connectivity logically first needs a proprietary access point. And one of the problems, and thinking what Mikkel was saying as well about industrial environments, well, in the case of medical devices, the world is very small. There are very few, 3, 4 large manufacturers that have all of the market, really, with very large market shares, a very restricted market then, and with rather restricted access to information, with very few players, which means that it's much harder for us to find out exactly what is going on. So what's required in the case of the pacemaker would be the device, then an access point, and then something like a router, which can't travel or move, is static, although more and more manufacturers are beginning to offer mobile access points. You would need to carry with you something like a mobile phone, and that way what happens is that the pacemaker sends information to the access point, and that the data then go to the cloud, to a proprietary point, as I said, and that information then goes to the doctor or to the hospital. When the pacemaker is implanted, it first needs to be configured, and back in the day, in the 1960s, that meant that in the operating room you would have to have all the IT equipment with all the problems you can imagine for hygiene and sterilization, which is not the case anymore. You can have all that equipment in a room next door, for instance, thanks to wireless connectivity, which makes surgical hygiene far easier. Can these devices be attacked from the point of view of security? Absolutely, they can. That's the case. And even though there are less devices to be attacked than in other fields or industries, but still they can be attacked. On what type of attacks are we talking about? Well, a long list. Although the attacks that we know about so far have mostly been labs being attacked. I'm going to tell you about some of those cases, because many of the IMDs transfer information that's encrypted data, and then how is that information encoded? Well, you would go to the lab, you would go to get the oscilloscope, you would look into it and find the coding that's used, because sometimes they're conventional encoding systems, sometimes proprietary systems. Some are harder to crack than others, but it can be done. And then, logically, you would be accessing very confidential information on the patient. Devices can also be reprogrammed. Look at this case where an insulin pump was reprogrammed, and using fairly simple hardware, an Arduino motherboard and an antenna that was kind of finely tuned to do something else. We would be talking about 500 megahertz in that case, not the same as for wireless systems, but again, it can be done for insulin pumps, together with reverse engineering, just to check which codes can be understood and followed by the insulin pump and which ones can't. But the main problem in this case was understanding in reverse engineering what kind of language this device can understand. Once you find what language it can understand, then you can do most things. So that's the situation with an insulin pump. What about a pacemaker, which is more critical? If you can send it commands that the pacemaker can accept, well, you could simulate and provoke a heart attack for that patient, or a neurostimulator. For instance, if a patient has a very severe tremor, just simply by deactivating the neurotransmitter, the patient would suffer from very, very severe tremor again, or anyhow, quite dangerous situations, or having a very high voltage applied. Just by switching the device on and off, that also hurts the battery in the device. And why can that be critical? Because it's a device we have in our body, and in a pacemaker, for instance, a battery tends to last for 3 to 5 years. That's the life. But if you make it switch on and off continuously, the battery life would be shorter, and then if you need to have it changed, that would require a surgical procedure, which is not a critical procedure, but still it has associated risks. I will talk more about batteries later on and why wireless should or shouldn't be used. But anyhow, batteries are fairly critical for these systems. When security and safety solutions are designed for IMDs, you might be thinking, well, why are they so different? Why not just use normal security mechanisms that we're familiar with? And I often say, well, you can and you can't, because the main difference here is that firstly, we need to think of the patient's safety, and only as a second factor, we need to think about ID security. So, for instance, computing capabilities and memory and battery, they're all fairly limited in IMDs, so we need to bear that in mind. When we talk about safety and security solutions for these devices, we need to strike a balance amongst all those elements. So let's go back to batteries. I said how these batteries tend to last for 5 to 10 years. If they need to be replaced most of the time, that would involve a surgical procedure, although some of these devices can be recharged overnight, for instance, through a wireless system. Why is that a problem? We do it. We can do it, for instance, with mobile phones. Well, in the case of IMDs, because the device has been implanted, we don't know really if that wireless recharging of the battery might have a negative impact on what organs or biological systems. We don't know. We need to look into it, so we've got that doubt. Some IMD manufacturers, as I said, have been launching products with this system, but it's still quite risky. What about memory? Well, IMDs have a fairly limited memory for storage, and storage means, for instance, keeping what's been happening for cardiovascular events during the day. Why is memory limited? Because if it was greater, it would need more power. So computing and communication capabilities are also limited in IMDs. And let's not forget how communication is quite critical here. And why is it so limited? Because, again, it's power intensive, and if it was any greater, then the batteries would last shorter. So, again, whatever security mechanisms we decide need to be added, we need to weigh the impact that will have on battery life. If wireless recharging of the batteries was improved and safe, that would be very interesting. This is an adversary model with active and passive attacks, which can be possible in IMDs. What can we do for protection mechanisms? Basically, we would have our traditional mechanisms, although in this particular industry, they need to be well adapted to these devices. Some of the solutions that I'm going to be telling you about have to do with biometrics. I've brought you two examples then. Here we can see biometrics based on ECG, which is the system that we know best about. When we design an authentication system, we can use something that we know about, a password or a key, something we own or have, like a smart card, or maybe a fingerprint or some biometrical signal. In biometrics, systems should always be universal, unique, only identifying me and nobody else. It should be permanent over time. It wouldn't change over time, although signals, biometric signals, are not totally, absolutely permanent since we're born until we die. Systems will have to be updated every so many years, but still fairly permanent, invariant over time. Systems should be collectible, reliable, with signals that can be attained easily, and then, as I said, well, obviously reliable and acceptable. Let me focus now on ECG signals. Here we can see a heart. What are we measuring then? Well, we're measuring electric activity in the heart, specifically action potentials that heart cells have. Here we have different waves then that can then be added and finally give us the ECG signal, made up by different waves. The P wave, then the QRS complex, then that peak you can see there, R equates to the heartbeat, every beep, as we say. And then the two final waves, one of them is the T wave, which is the one that we're going to be monitoring and playing around with. I'm going to tell you now about a piece of research that wanted to use compressed ECG signals for authentication purposes. Before I tell you about this study, I want to give you a little bit of information about biometrics. When we work with signals, we can work either with time or with a transformed domain. Here we can see the different points and the peaks of the signal, peaks and valleys, difference in time between the peaks. Is that easy to calculate? Well, it is, but it's very time consuming.
And that's why some other people think instead of using time, what about frequency, which seems sometimes to be simpler. If we talk about frequency, we have so many transforms that help me transform that temporal signal into the frequency. We have Fourier's transform, one of the best known, Weiler's transform, quite fashionable now, and we use Walsh-Hadamard transform, and I'll explain why. Why did we put forward this Walsh-Hadamard transform? We wanted it to be very efficient in computational terms. It has to be a solution that will be embedded in a very limited device, so we really want it to be easy to be computed, and actually this is what we get out of WHT. WHT is multiplying a matrix times signal. So you have ones and minus ones, so it's quite simple to calculate this transform. And then this feature is not exclusive to the WHT, but it compresses signal. What does it mean that it compresses signal? Well, it gets all the information that it would be the first coefficients or ratios of the signal, and with that we have all the information. And so it helps us rule out or despise, so to say, the remainder of the signal. This is important because with a compressed version of the signal we get it all. So this is a classical biometrical system. If you are not familiar with biometric system, on the one hand we have the sensor. The sensor can be the IMD that it's inside of us, or it could be a sensor with some probes or electrodes or LEDs or electrodes on the body. So this looks like an EKG, but usually lots of noise and ups and downs, etc. So for this we need to have a pre-processing of the signal. So we need to clean the signal so it looks like a textbook EKG, after which we need to mine out some features. In order to extract or mine out the features, well, we have two options. I've already said that. First we go to time domain or then frequency domain. There's also an option of mining features in time and frequency both and then combine them. Actually, we chose something simple, that it's only frequency. Then we have what is machine learning, a classifier, and we have so many different classifiers here. Then I'll explain that we use a simple approach theory, but works very nicely and it's not too complicated. This would be the system. Basically, with these kind of systems, we have the pre-processing. Typically, at least you need to do a couple of things. First, remove the continuous stream and then have a passband filter to remove most of the noise that we have there. These are the typical parameters that we handle in order to read an EKG. And then something else has to be done. Well, you have an EKG, which is a continuous stream that has to be segmented, so split into parts. Here, what we did was get 2-second windows. And you might ask, why 2-second windows instead of less? If you take into account the heart beat of a person, the heart rate of a person, a man or a woman, for the average rate, we wanted that window to have 2 bits. Why 2 bits? Because according to the literature, it is quite simple to characterize a biometric system using EKG using just 2 bits. And that's why, and taking into account our sampling frequency, we got 2 seconds or 256 samples. And so this is a transform, this is a sequencing, and this is a coefficient. We got every test, and we saw that just with 24 ratios or coefficients we can characterize the signal. You need to understand that we moved from 256 samples that we have for time to 24 ratios or samples for frequencies, so it's quite a significant reduction, right? And then we also check whether if we're adding something else, that's entropy values to the signal, and see if with that we could improve the identification system or not. This is what we put forward for a system. As classifier, I said, so if you've learned some machine learning or you're familiar with it, there are so many options. Here we used a very simple one, which is a KLD, a non-parametric and vague system. And why did we use it? Well, firstly, because it's simple and easily implemented, and secondly, because there is no guessing about the data distribution, which is good. And why does it not? Well, it doesn't take any training. For this, there is no training. Only thing we need to do is store the sample and then compare your new sample to what you had. There's this, with the KLN, there's a parameter, see how many neighboring values you will check for the classification here. We looked into several configurations, and even with just one neighbor value, it would work. Usually 3, 5, 9 neighbors, it was enough, but we didn't have any significant improvement as to increase the complexity of the system. So what dataset did we use? In order to check the system, we used a dataset which is well known one. There's a database, a large one, known as VisionNet. And there, if you are into this topic and you want to go deeper into it, you have so many data sets and you can have so many signals there. Here, I said there's this one. Why did we choose this data set? Basically because it has EEGs for 24 hours. There are not so many data sets where you monitor the subject for so long, so this is one of the largest data sets. And then on the other hand, it is also that subjects have no severe heart disease or condition, no significant arrhythmias. So here we have to say that this dataset, it is true that it's great for experimenting and for the early testing, but you need to take into account that the subject, that is, people are in ideal conditions. They are standing still or lying down. And usually this data set has been with 7 to 9 electrodes on the subject, so this is ideal. You also need to test this with a hostile environment where the subject develops different activities and moves around, and where there's no 7 electrodes, but usually the typical 3 electrode configuration, so there will be more noise in the signal, that's the kind of thing. So you really need to play around not just with this kind of data set that is for a clinical environment, but also for a more realistic daily life environment as well. Let me show you, without going into detail, what the results are. And so, depending on whether, so we have 2 options, 1 and 2. Option 1, we only use Hadamard ratios, and then Hadamard ratios and entropy in the second step, and there's a significant improvement, as you see on the screen, but not that big. So we are somewhere around 95-97% of accuracy, so that means that it works quite well. This is a first approach, a classical approach on how to solve the biometric authentication problem. And next, what I wanted to say is one of our recent works. I don't know if you know about authentication systems, continuous authentication systems, but the previous system is a classic system for non-continuous authentication, where the user, for example, non-continuous authentication would be you get authenticated once. For example, when we log onto the system, you set your user and password and you don't need to authenticate yourself any longer. For continuous authentication, that's more demanding because the user has to log in every given time. That given time will be set up in the system. It can be chosen every 3 milliseconds, every 3 minutes, or whatever the parameter we choose. But there we check continuously and we make sure it is a legitimate user, and it's quite a significant difference. For this kind of solution, problem is that classical techniques for data mining or machine learning, well, they do not work. It is true that the classical ones help us deal with large data sets, but we cannot treat with this concept that is known as data stream mining. So the data stream mining, it's a new area of artificial intelligence, and we can treat signals in a continuous way. So what are the features of this kind of systems? First difference is that signals, or the samples we have, were only done once. Then another important feature is that the number of resources is very limited, both for memory, both for working conditions. If we compare a classical session with data mining, if you have training and testing, the training and the testing data set, it can all go into the memory, it all fits in. And then for a data stream mining, the data set and the testing, there's no testing or no training. The testing and training would be just one, and it's all fused together. So I cannot tell apart what's testing and what's training. Problem is that I get samples on a continuous basis, which means every second, every millisecond I get that, and that's indefinite. It seems the process starts and never stops. That process seems to be infinite. And then another feature that I have to take into account has to be immediate. I might have a system, but that system needs to predict. I need to get a sample, and I need to be able to predict it that very same minute or moment. This would be the greatest difference between the previous system, which is a bit more static, and this one is a bit a time series that evolves with time and it keeps feeding on a continuous basis. For this to happen, there is new field in artificial intelligence, data stream managing systems. It's a different way of processing. The system that we put forward, well, some are similar to what we had, but so we have the sensor first, we have the pre-processing and the feature extraction. Originally, this would be the same as with what we had with the previous proposal. Then we will see whether it is just the same as what we proposed. And then we had, if we forget about the similarity module, we would have what's known as the learner, the learning system. Here it will be a learning system that can be based on learning systems for data stream mining, or data mining rather, that we know, but they need to be updated. They need to be transformed, that is, in order to use it for our new paradigm. And as I was saying, we add a new module that we called the similarity module. And what we say here is that before feeding the system, we wanted to say, do not add samples into the system that are too bad quality. So we discard those that are too bad. That's what we did with the similarity module. So without going deep into it, processing is just the same. And then feature extraction, we used Hadamars, but since the system is a bit more demanding, because I'm checking the system every few minutes, I need to better characterize the signal. And for that, I need 256 coefficients. The compressed version is not enough. I need all 256. As for similarity, basically, here we have a very simple model. This is the first approach, is a correlation model, and that would be it. The idea is to rule out samples. As for the learner, we basically use, we use a KNN. KNN, which is simplified and with a limited memory. This is a sliding window, as it is called. Basically, we only keep in the memory what's the most recent sample. It makes sense because in the end, what this means is, or what these systems do is they adjust to the changes in our time series. This would be an EKG, and it seems that our EKG is better characterized with the most recent samples. And this is what we keep in our memory, but this is a very limited memory, okay? So, for the memory, you need to consider that we used different approaches. We use the buffer and unbuffer. So we analyze the system, a high demanding analysis that is, that where we check the system every 2 seconds, 2 seconds that is, and then we have the buffered approach where we check the system every 3 minutes. So it is real time, well, not real time, but every few minutes, and we have a larger regular time interval. So this is what's shown here. Basically, what you see here is how the system behaves if the authentication is every 2 seconds or 90 seconds, that is 3 minutes. If it's 2 seconds, the accuracy, well, there is some slight deterioration down to 80%. Not bad, but relatively low. And so if we're less demanding in the system, we manage to get the accuracy that we were having in a classical system, around 95%, which is a figure which is much more relevant. As I was saying, the greatest difference here is that what we're monitoring real time, and the other great difference is that the memory that the system needs is way lower, so it can embed these systems in limited systems because you don't need that much memory to keep working. And same as before, YKLN here, it is because it is simple and it takes little computing power of the system. And next what I wanted to say is, well, okay, so far what we had is we can have authentication systems, whether continuous or not, which are EKG based, but then we thought of the future and we said, okay, can we improve the system? Can we put forward a system that is better if we're using, instead of one signal, several signals? That was known as a multimodal system, and this is what we did here. So here we have a prototype. It is homemade, and you see that. Well, it is low cost, clean, so it's not too easy to move around, but it is a lab study. So it's a test. And basically, what kind of signal would we get? We would get the EKG, PPG, the accelerometer, and the GSR. 2 hot signals, motion signals, and the galvanic answer, which is usually used by those who work with motions or emotions. Biometric system. Even if the figure it looks better, this is the classic biometric system. There's nothing new here. What kind of signals are we using? Well, as I said before, and the features, same as for EFG, accelerometer, or PPG, same back to frequency. And we were not sure to see whether we were using Hadamard's or Fourier's transform, just to see if one was yielding better results than the other. But the GSR, I don't know if you've ever looked onto a GSR signal, but it's quite simple, not much in fluctuations. And we see that with some statistic metrics, we can characterize it quite easily. It doesn't take much more than that. As for the classifier, there is a basic difference here compared to previous proposals, and that is that what I've said so far, we've followed a classic approach of data mining. You have a 10-subject data set, and that data set, you split it into training and testing, and you have 10 subjects on training and 10 on testing. That was usually done with data mining. But if you're thinking of a system that you want to train with your own signal, first you get your signal, and then you got your signal and everyone else's. But initially, I don't have a signal from anyone else. If you want to train your phone with your heart signal, you need to use your signal, not anyone else's. And so we used the one class classifiers where for the training we have one signal, one subject, and for the testing we have a set of subjects, the target, and some more. That's what we saw here, and the advantage here, okay, what we've done, one of the advantages or main differences compared to the previous ones is that so far, and it is a weakness or a deficit in many papers, but in most of the previous papers that I've introduced here and also of others are based on data sets that are limited to the medical environment because that's what's available. So now if you want to do something and you don't have a data set, the databases we have are from a medical setting. So we produce our own data set, quite rudimentary, but it would allow us to look into several things. First, here we have several activities. This is activity number 1, when the subject is standing still. Activity 2, when walking. 3, when they are standing still, but just after walking and back to sitting. We wanted to see how the system behaves for several activities and how it behaves if trained for activity, and then test it in a different activity, which was not allowed by other data sets. Here you see, that's not the accuracy. You've seen this the other way around. This is the ER, that stands for error in the system. Probably, well, you don't see the scale, but what we're interested in is having a figure that is as clear as possible. We have a pale yellow in so much as possible. If you have one single signal, the EKG is what works best, and we already knew. And so this contributes to our theory. And other signals, PPG, GSR, or the accelerometer in themselves do not work, so it's better to combine them. And here you have a combination of all those signals, and typically if we combine, I don't know, for scenario 3 and we combine PPG and GSR and others, we have good accuracy and good error levels. Which means what? Well, the conclusions we can draw are that it seems that if we combine several signals, well, it's not that it seems, we see that from the results. If we combine different signals, we improve results. It is true that with EKG we get better results, so it's a slight improvement. So what I think is that we need to be heading towards combining different signals. And why that? Because actually in most cases our body, whether inside or around us, we have a series of senses, and it is about tapping on the potential of all those signals that we get from the sensors. So just let me discuss a few conclusions for medical devices that are implantable, so IMDs. Are a reality? Yeah, that's true. The new generation of IMDs are already out in the market. Most producers, or almost every producer, offer this IMD with wireless connectivity. It is a reality. It is true, though, that is a reality for some IMDs, for pacemakers, everywhere, for simulators. There are some manufacturers that add it, but not all of them. For insulin pump, yes, they add these features, so it is a reality. From the point of view of cybersecurity, it is a very serious problem that we would need to approach from the design stage. I would say my main criticism here is how restricted this is, how difficult it is to have access to information, how difficult it is to gain access to manufacturers. We do have experience dealing with several manufacturers, trying to gather information, trying to have devices, and reality is that most cases it's a negative response and only little information. Why is that? I guess that they are risking lots of money and are not willing to crack the melon open for a security analysis. And the thing is, whether they crack them themselves or someone else, the reality will be found. So it's all about spilling the beans. So one of the main things that it's saving us, it is that nowadays, if we want to be treated with a pacemaker, it is not easy to get one. And if you have to buy it, it is somewhere from 6,000 to 12,000 euros. So we will not just go on eBay and buy one. So it's difficult to buy. And so the research is moving slower than we would like it to. As for pacemakers, you need to be in contact with hospitals and doctors, and then through them you will gain access to devices or information of that kind. And from the point of view of biometrics, it is true that biometrics a few years back, well, we've known for many years now, but it is true that in recent years there's been some progress in this field. But I guess all new techniques for data stream mining, deep learning, it can all help design new security solutions for this kind of devices. But we need to know whether it will be embedded or not, if there are things you can do with it. And then my proposal would be that we move on to a world where it is not just a single signal sector, but a combination of signals rather, and that will make things easier, lower error, greater accuracy, more stable systems, etc. So thank you very much for your attention, and if there are questions. What about state of security in devices, implantable or not? There was one looking into brain waves. And so are you working on privacy of data, which are not medical setting per se, but there we would need security, right? Security measures, because it's about health, but about privacy as well. I do agree. On the one hand, safety, patient safety that comes first, but then security. So safety and security come in hand. And we need to protect as well the privacy of information, access to information and everything else. What do we find now? Well, reality is that most of the devices out in the market do not give that. The problem is accessing information. So if you take the data sheet with the manufacturer's description, they'll say that it's a safe and secure device with the mechanisms in place. But truly what we've proven, this paper just a few months back with some investigators or researchers looking into every pacemaker from every manufacturer, and the same conclusion is that barely any security measures are taken. As for brain devices, whether implantable or non-implantable, I don't know which one you're referring to. Some come to mind, but most of them, I would say, there is no security mechanism when there should be some in place. Thank you very much. But is there a model, kind of the Geneva Agreement for regulations on attacks on devices, very closely linked to patients' lives? I'm unaware. If there's anything, as you say, with the Agreement of Geneva, but there is a law in Europe for privacy that needs to be complied with, and it's basic. And if information is on plain text, it's not being complied with. So these are things, basic things that need to be done and are not being done. Why? I don't really know. I would say the main problem nowadays, well, phone manufacturers are just focusing on patients' safety and improving the quality of life of their patients. That's it. But adding wireless connectivity, it is a huge paradigm shift, and this opens new doors, and that's what they need to focus on now. And I'd say they are not paying attention. And main problem, as I said, is the interface, how they will communicate with the manufacturers. There's only a bunch of them, and it's a very limited environment. So we published a revision. This was Carmen's first attempt on her dissertation, and there was an interview for a journal, and the next day, and it's been months that we had been trying to talk to some manufacturers, and the next day we got calls from every manufacturer because we were saying that IMDs were not safe nor secure. So there's money at stake here, but only when you think that their business might be compromised, that's when they worry. If you ask me, I hope this changes. And I hope they include security measures as they should. But what about the battery? Battery, I think it's critical as well. And everything you do will reduce the battery. Thank you very much. I'd like to know if there is a specific use case for which you need continuous authentication. IMDs that would need it to guarantee the continuous authentication of users. Well, it depends on how critical the system is. There are systems that require authentication. Actually, there's this one company that is selling a CA system that is based on EKG. It seems to be a continuous authentication for your home. This is for a dramatic house where you are present, stating what you can do and cannot do. But I'd say that the authentication methods, continuous authentication methods, not just heart rate, but that's where we are headed. So if you think of your cell phone, it does check. So instead of locking and unlocking, well, somehow making sure that you are there, that you are who you say you are, but actually there's nothing you need to do. So it would be a much more transparent system for the user, but making sure that the user there is legit. There's another question. So biometric systems such as footprint or retina scan, could they not be replaceable here? The retina scan is very reliable, but problem here is invasive.
That's probably why it's less popular than the fingerprint that has been going for quite a few years. What's the main difference between EKG or ECG signals and the fingerprint? Well, with ECG systems, you might wear, say, a T-shirt with sensors, and that's not science fiction, that's being manufactured. And that would be measuring not just your heart rate, but all of the biometric parameters. That's a very rich signal. And not only that, that's transparent as far as the user is concerned. There's no need for continuous interaction where you don't need to keep your finger or your hand on a particular spot every so often. So those biometric signals are very user-friendly, less invasive, and easier for the user. Any further questions or comments? If that's not the case, I would like to thank you once again for attending my presentation. And if you think at a later date of any doubts or questions, please get in touch. I'll be very, very pleased to give you more information about this particular topic. It's not just me doing this research. It's a group of us. And we are currently still it is still underway. Thank you for your attention.